for the people in the Zoom, there is about 50 candidates also in the Zoom. So I will introduce Mr. Aingaran again. He's director at Nvidia, who is leading the semiconductor division, as well as former Googler, who has helped Google in terms of the tensor flow processing units, TPUs. An industry expert from this area who has been actively leading hardware side for ML purposes. So his talk is going to be about building modern AI systems from CNNs to ChatGPT. And as I told you already, he promised to give some inside stories, fun stories for us to learn from what happened in the industries and how that paved the path today. So over to you, Mr. Aingaran. Thank you.
Thank you there, and it's really great to be here. So that's the first thing I wanted to say. It's when I was a teenager, this is where I dreamed of being, and that didn't actually come true in terms of my undergraduate studies, but it's great to be here now. So thank you for this opportunity. I'm going to do the rest of my talk sitting down, if you don't mind. So the next thing I wanted to say was this is not an NVIDIA presentation. So I am working for NVIDIA. I'm happy and proud to work there, but this is not an official NVIDIA presentation. This is done as purely as a personal capacity. So don't take anything I say as coming from NVIDIA or any of the other companies I have worked for. So this is the. Are we missing? Okay. Okay, thank you. So this is the agenda for today. So I'm going to go over a very brief timeline of how AI has evolved in the last 20-ish, 25-ish years. And then my talk is going to be focused more on the hardware side, because hardware is what I know better than the software and algorithm side. Hopefully, it's something that you find interest. And when we talk about hardware architecture, there are four essential concepts that are involved there. So one is the part that most of us focus on, which is the computation itself. The operations you do, how fast you do them, what you do, what sort of data formats you operate on. But that's only one out of four pillars of computer architecture. The second is your memory structure and how you handle storage, how you handle the state that you need to operate on. So things like caching and memory hierarchies and all that. And the third one is the communication architecture, how different compute elements talk to each other and how they stay synchronized and consistent. And the fourth one is not really traditional computer architecture, but it's a fact of life today, is how you handle the power dissipation. Because all systems we build today, they're limited by the amount of power that they can burn. So you have to invest that power appropriately or in the most efficient way. So the power architecture also becomes important. So for ML systems, I'm going to be talking about how these four aspects of architecture influence the rate, the way at which the systems evolve. And then I'll talk about some challenges going forward. And finally, the last bullet, speculation about the future, is something all of us like to do. I actually don't have any slides on that, but maybe after I'm done, we can interactively go into that part. Okay, so brief history of AI. So it started with the realization that you could do things like linear regressions, which can replace an algorithmic, deterministic algorithms with something like linear regression. So an example I like to show people is this video, which some of you might recognize. Unfortunately, there's no volume, but if you look at this stroke, go. Okay. Are we sharing the desktop? Oh, I see. Yeah, we have to move it to that screen, I think. Yeah, we just have to move it. How do I get rid of it now? You know what? Never mind. We'll script that part. Let me skip that part and we'll continue. Anyway, what that video shows is Sanat Jayasuriya doing what he does best. And so just imagine it, but it's this ball that's bold, and all of us, who have studied engineering, if someone tells us the velocity at which the ball is bowled and the angle and all that and the wind resistance and the property of the pitch, we can calculate, with the appropriate differential equations, we can calculate where it's going to land and rise and where it will show up. But Sanat is able to calculate that without doing any of these equations, right? It's not a deterministic algorithmic process. And instead, just by the eye, he's able to determine it, and he's able to play that stroke at the right time. So this is what I mean by sort of non-algorithmic. It is algorithmic in a sense, but it's not a deterministic algorithm following certain steps. Instead, it's more like a regression where you have some data, you try to fit to it, here's some data about where the ball is. He has seen it many times, practiced it, so he knows he can predict where the ball is and he can play the stroke. And that's the basic, the fundamental shift in compute that's happening with AI, is we are going from things that, in computer science, we traditionally learn in terms of number of steps and complexity and all those things, and all of that is thrown away in terms of something that's more like an estimation, pattern matching and statistical estimation. So that is nothing new. It was known in the 1950s itself. And from that evolved, basic perceptrons and classifiers, which, those of you who have taken a machine learning class would be aware, what we do is we have a certain input, we feed it to a model, the model makes a prediction, and then, we have an expectation of what the prediction is, and based on that, we tune the model until the prediction matches what we want. So this was also, again, before the 90s itself. But the thing is, they couldn't do anything useful with it because we didn't have enough compute power to train any useful models. Then in the 2000s, finally, we had enough compute power, and some very smart people built this thing called AlexNet, which was a convolutional neural network. And convolutional neural networks take a huge amount of compute compared to even the perceptrons that were used before that, because you're essentially moving this convolution window throughout an entire image or an entire time series. So this was made possible in the 2000s, and finally, we started getting very interesting results. People could start identifying cats and dogs automatically and so on. So then the next interesting step was with autoencoders. So for those of you who are not familiar with it, autoencoders are essentially something like a compressor. They can take an input and condense it down to a small model, and then without looking at the input, they can regenerate it. So you can think of it as some sort of compressor But this was the beginning of what we today call generative AI. So you take something, you compress it down to something that we don't understand, is nice and small, and then again, it's kind of like if you see a dog, your brain registers it as a dog, and then later on, if you have to draw it, you can actually draw the dog reasonably well, even if you don't remember all the details, because you know what a dog looks like. So those were the autoencoders. At this point, something interesting happened. There were some researchers who were bored, and they took the traditional training program they had, where, as I told you before, that you take an input, it goes through a model, it makes a prediction, and then you go and update the model. And instead, what they did was they moved this arrow back to the input. So they fed an image, and the model said, there isn't a dog in this picture. And they said, no, yes, there is a dog. Go and modify the input the way you would have modified. So it went and changed the input. And after some time, this random image became the image of a dog. So they did this for fun, but they, again, they had taken unwittingly the next step in generative AI. So now AI was actually capable of drawing pictures on its own. And this was a huge step. And again, the reason they could do it was because they had so much compute to spare that, for a hobby like this, they had enough compute lying around. So this led to what we call GANs, or adversarial networks. And in this case, what they did was, so the dog that was created in this first example, it was a toy experiment. After all, it wasn't a very convincing picture of a dog. So then they took that generator that generates a picture of a dog, and then also a picture of an actual dog, and they fed it to something called a discriminator model, which can tell the difference between a generated dog and an actual dog. And they train both at the same time. So you train the discriminator to tell the difference, and you train the generator to beat the discriminator. So this is why it's called an adversarial network, because they're working against each other, but they make each other better. And so we were able to build much better generators that could draw very convincing pictures of a dog. And that's what has ended in things like Midjourney today, which, as you know, can generate extremely convincing pictures that you can't tell that they are not a photograph, or you can't tell that they were not drawn by human artists. So parallel to this, we had another advance in terms of speech processing, which was embedding tables. So this is also something that was known for a long time, but any meaningful embedding tables take a lot of storage and compute and memory bandwidth. So embedding tables, essentially, they take a word and they try to map its meaning to a multidimensional space, like given here. And you have to train the table to have the right meaning, but after enough training, you can actually map it meaningfully. So today, Google uses something, a few hundred dimensions in their tables, and they use about 30 tables, I think. And OpenAI uses similar dimensions for their embedding tables. This was originally meant to be for words, but now they're using it very creatively for other things as well, even for gene mapping and image analysis and so on. So it's a way of capturing meaning, and it seems to mimic the way that the human brain also works. So then came the next advance was in 2017, is this program called DeepMind. So how many chess players are here? Anybody? No chess players. Or nobody wants to admit they're a chess player. Okay, anyway, so DeepMind is the initial one was a chess playing robot and chess playing AI, and after that they built an AI to play Go. They built an AI to play Go, And the insight that they brought was that they once it was fed once the input was fed to the model, it was capable of generating possible future states, and therefore it was able to analyze what could happen in the future. And previous chess-playing robots did an exhaustive search of the future, which was not very efficient and it took a lot of time. Even though IBM's Deep Blue managed to beat Kasparov before this happened, but it was still not that great because it was doing an exhaustive mechanical search. This was able to do a future, it could generate a future of actual moves or actual good moves. And based on that, it was able to make even better decisions. And today there is no human who can even come close to beating the DeepMind robot. So then the final piece of the puzzle came in 2018 when transformers were invented. So before transformers were invented, speech and any kind of text processing was done serially, the way the human brain does it. When I talk to you, I put the words in a certain order, and if I jumble up the order, then I would make no sense to you. And so it has to be processed in that order. And NLP models were actually processing things in order, and then someone had this insight that you could instead build an AI network, an ML network that actually accepted the input in parallel. And they, along with this parallel input, they've found a way for the model to focus attention on a variable amount of text. So it's able to, you feed, for example, an entire sentence or an entire paragraph in parallel to it, and it's able to expand the scope of attention up and down, and you can train it to spot the area where it has to focus attention on. And attention is mathematically defined very carefully, but I'm losing it very loosely, using it very loosely here. But it's similar to human attention, and it's a question of where the model focuses on. And you can train it to focus on the context of what a person is saying. So previous translations and all, you could always type a sentence that the translator would get wrong because you write it in such a way that the context is spread over a very large sentence and it won't get it. But after transformers, it can understand the context even if it's spread over an entire paragraph. So it's that was the final piece that made something like ChatGPT possible, that now it can carry out very convincing conversations with not audio, not with audio, but with at least in text. So then, these generative chatbots came along, and not only can they understand, but they can also generate responses. So let's look at the computation side of it. So how does computation, how have the computation requirements evolved? So it turns out that most of the compute that is necessary for everything I described so far is pretty simple. It's mainly doing dot products and multiply accumulates. And of course, there are some nonlinear ops that have to be inserted because you can't create you can't model a nonlinear function with just linear regression. So there are some nonlinear ops, but they are not in the critical path. It turns out that the linear operations take a lot more time than the final activation step. And then there are also similar normalization steps and distance applications, but even these essentially multiply and add or subtract. The interesting thing about all this compute is that it's data parallel, meaning they are not dependent on each other. There's a huge amount of parallelism, so you can do things at the same time. And in a way, it's like our brain as well, which does a lot of computation in parallel. For example, if you take a CNN, all the convolution windows can be done in parallel if you have enough hardware to do it. So that's what this graph is showing, is how the hardware has tracked, how the hardware requirements have changed over time. Like, and you can see as soon as social media comes in, we have so much more data, we are able to build all these fancy networks, so the requirement has just shot up. And over here in the next graph, you see how actual hardware is doing, which is much more linear than this. So this is this curve mapped to this is this black line. So you can see now the requirements are going past us. So what we are doing is we are building multi-chip systems now, multi-GPU systems to keep up with this. So this gave rise to companies like Nvidia and custom TPUs from Google and so on. So there are two kinds of compute structures we use. Like, so I already said the compute is pretty simple. One is the traditional GPU, which does multiple things in parallel. It has these many small cores. They can take an instruction. They are quite flexible, and you can spread your problem across all of them. And then there are chips like the Google TPU, which use a systolic array, which are much more limited, because they said, hey, if all we are doing is multiply and add, why do we need to support anything else? So they built this very dense multiply add units, which and then for some, and they built it in the time of CNNs, and then they pushed through millions and millions of CNNs through it at very high efficiency, and they were able to even beat GPU performance based on that. So after that, you saw that even Nvidia started putting in what they call the tensor core, which is a smaller, not as big as Google's, but a smaller systolic array inside each of their GPU cores, specifically to speed up something like matrix multiplication. And the interesting thing is, not only is the compute simpler, but the algorithm itself. Now, CPUs, if you look by comparison, they have very complex branching units, scheduling units. There's so much that goes into scheduling instructions that it's the overhead of that is more than actually executing the instruction in, if you look at the chip in your phone or in your laptop. But all of that is built into the ML architecture, the architecture of the AI network. So there's no such thing as branching, right? If you need to make a decision, then it's just a weighted sum. Where if I want to choose A or B, I multiply, and let's say I want to choose B, I multiply A by 0 and B by 1 and add them together. So there's no external decision, it's all just mathematics, all just multiplication and addition. So then the question comes, like, is that all there is? So in the 2010s, there was this big debate of people who said, no, there must be something more, and people who said, no, this is all that's needed. And as proof, if you look at the human brain, the human brain seems extraordinarily homogeneous. The cells in the brain that do one function seem capable of doing another function as well, and they all look the same. The part that does hearing versus vision versus thinking. And in fact, we'll see that, for example, blind people, their visual cortex processes other things like hearing or critical thinking, for example. So that shows that the same cells are capable of doing all sorts of functions. So this was a debate that was there until transformers were invented, and after that, it sort of settled the debate because they seem to be capable of doing everything. So right now, it's more towards like, yes, this is all there is. So the next part of compute is data formats. So one of the observations with ML is that a lot of accuracy is not needed, because all of these they're approximate, and a lot of the noise gets weeded out during training, and there are so many components that go into it and so on. So people started experimenting with number formats that were not as precise as before. So if you look at a graphics card, they support double precision and single precision. But then at some point, Google said, you know what, we can use lower precision than that. So they went to 16-bit numbers and 8-bit numbers. And you can see in this graph, obviously when you make the number smaller, you can pack more arithmetic into a certain area in a chip, and therefore you get better performance. And so this is an area of very active research right now. Good question. So that's actually a good example into the next slide, or put the intro to the next slide. So one of the problems that we ran into when we started cutting precision is we started rounding numbers a lot sooner. So if you're doing large summations, this turns out to be a problem. So let's say I have an addition like this. I'm adding 0.1 to 1,000 and I round it to 1,000. But when I go to a neural network, I might do this operation 1,000 times, in which case, my expectation is that the answer is 1,100. But here I keep getting 1,000. And this actually had interesting side effects because on language models, early language models, they found that exactly because of this. Now, English doesn't have this problem, but Asian languages like Tamil and Sinhalese and some other languages, the voice, we have a formal, respectful voice and a more informal, not so respectful voice. And it turns out that when this rounding problem was there, it was not using the correct voice when it was talking. So it was being impolite and rude in certain languages. So this was, it was somewhat of a funny side effect. And after this, the need for mixed precision was found. So they started saying, okay, just when we are doing the summation, we'll use, a more precise format. And there are other times when we can use a less precise format. And similarly, when you're just doing inference as opposed to when you're doing training, you can use less precise formats. This was also the time that they invented stochastic rounding, which was a rounding mode that is, it's not used in high-performance computing, but it's used in machine learning, where the rounding is more like a Markov process that picks one or the other based on the number that you're rounding. So, for example, if you're rounding 0.1, then with the probability of 0.1, it pushes it up to 1,001, otherwise it's 1,000. Now, if you repeat this 1,000 times, you get an answer that may not be exactly 1,100, but it's close to it. So this is the mode that's actually used in most machine learning systems today. So then memory speed becomes a bottleneck. So, we have this, the compute and memory, and what we did was we made the compute bigger, so obviously now memory has to keep up with that. So to get memory to keep up with that, several technologies are being looked into, but the one that won out is mainly what we call HBM, or high bandwidth memory, which is just DDR stacked on each other. And it's pretty fast. It's incremental over the existing technology, and it seems to have won out over other more fancy technologies. And the access type until we got to word embeddings was very simple serial sequential accesses. But after word embeddings, we started getting more sparse data. So you couldn't just serially load entire embedding tables, because when you take the meaning of a word, if you look at something that's 100 dimensions, most of the dimensions will be 0. So there's only a few areas where there's meaningful data. So we needed to have better random memory accesses as well. So those two, so we have faster memory with HBM, and you can see, for example, this is the Nvidia Ampere system. Right next to the Nvidia chip, you see these stacks of HBMs that they are using. But the price you pay for the higher speed is that you have lower capacity. So the other issue is that we parallelize. We said we are doing all this additions and multiplications across different compute elements. So then the question is, how do you keep everything consistent? For example, if you're updating a model and you're doing it from multiple compute elements, you may, the update from one compute element and the update from the other compute element have to happen in a certain defined order. If that's not deterministic, you have a problem. And normal CPUs are good at handling this, right? They have all this overhead to keep memory consistent. But GPUs don't have that. They're just built to run fast, and they don't usually talk to each other in this way. So this was a problem, but again, at some point, someone said, why bother? So this was quite a famous paper from, I think, 2013 or 14. It's called Hogwild, where they said the traditional rules of memory synchronization and consistency are not required. And again, it's going back to the fact that all these ML algorithms are very noise tolerant. You can make a few mistakes here and there, but it still converges down because you're running an optimization that walks down some surface to find a minimum point. And if any one step is off by a bit, that's fine. So this is actually, it was adapted, but there are problems that we are seeing with it today, and one of the things is explainability. So we need to understand why a machine is doing something that it's doing. And if it's going to behave a little differently each time because of the way that memory is consistent, that's a problem. That's a trade-off that we haven't arrived at the right trade-off yet. There's still arguments about that. But again, it goes down to the fact that when we build these things, the rules are very different from building CPUs. We can knowingly make errors and still get to the right answer and still have a reliable system. So the next issue with the memory architecture is how you partition the problem. And I won't spend too much time on this, but it comes down to how you split the data. So I said earlier that when we use HBMs, we are capacity limited. So the amount of fast memory you have is limited, which means that if you have something like 175 billion parameter model, which is the size of ChatGPT, or GPT-3, which ChatGPT is based on, you need to start splitting up the model. So it's just different ways of doing matrix multiplication. And in this case, you split it up so that the dark part and the light parts are done in different machines. And this is not really a hardware thing. It's more in terms of the software that is closest to the hardware, how it utilizes the hardware. And I'll get back to this later, that the future innovation is going to be in that hardware-software interaction, how the software uses the hardware. The other option is called batch parallelization, where you split the matrix this way and vertically and split it up. This is, you can see here, this is a graph from Nvidia showing how increasing the batch size gives better utilization of the hardware and better performance because they are splitting it up in this way. But for some reason, we are now moving more and more towards smaller batch sizes. There are other advantages to doing that, so this is less relevant today. So I spoke about the compute part, the memory part, and then the next is the communication. So in that first graph I showed, the hardware was keeping up with the requirements until very recently when things have gone up. And so to bridge that gap, what we are doing is we are putting multiple chips together in systems. So for example, the ad serving TPU that Google has, they use 64,000 nodes on this one thing that shows the different ads. That each time you go and search on Google, and it shows you some ad that seems to uncannily be close to what you were thinking about yesterday, is because those 64,000 nodes are working together to do that. So then the communication architecture that connects these machines together becomes very important. And that's right now an area of research, is how you exchange model parameters between these machines, how you exchange intermediate results. And again, this is as much a software problem as it is a hardware problem. It's about how you can partition problems so that you minimize the amount of communication that's needed. But for now, we are building, or the industry is building faster and faster links to connect these together. And so this is how things have evolved. Initially, you had a host CPU with a GPU tied to it, and that was good enough in the 2000s. Then we came to this where the GPU had its own fast memory because memory became a bottleneck. Then we started stacking multiple GPUs together. And now it's not just multiple GPUs, but multiple host-connected GPUs tied together like this. And we have custom interconnects or high-speed interconnects, some of which may be standardized soon, but they are high-speed interconnects. So the other is the power limit, and I think I am a little behind time, so I won't spend too much time on this. But there's as this graph shows, the power we can dissipate is pretty flat, but the compute we need is rising up to meters. So the challenge is to do more and more computation without burning more power, because there's only so much heat that a chip this size can take before it starts to melt. And there's also only so much current you can deliver into a chip that size before you have other problems with the supply. So already the chips are liquid cooled to remove the heat from there, and then we go to a lot of extents to deliver the right power to it. And there doesn't seem to be much more we can do in terms of extracting heat, so we have to be more efficient. And so that's why the metric that we use today to judge a chip is the performance per watt, because the watts are limited. So there's no point in getting high performance if you're burning too many watts. So this ratio is what we are trying to optimize for. So again, I will skip over this slide unless there are any questions. So then let's look forward to a little bit and see what are the challenges that we are likely to face in the future. So there's the first 3 points are more of the same of what I said. It's the power is limiting us, and if we want to go to brain scale, meaning if we want to do the same amount of computation that we think the brain does, we are off by a factor of close to 1 million already. And the amount of power that these 64,000 node systems that I told you before burn is close to the megawatts. So we can't burn more than that, right? And we know the brain only spends about 25-30 watts. So there's something here that we need to bridge. And then even if we get there in compute, because we seem to be at least on the right trajectory with compute, with memory capacity and memory speed, we still have a long way to go, and communication bandwidth. So these are areas where we can contribute. But more than that, there are other not so hardware-centered challenges. So one is fairness and explainability. And I said this before, is if you let the machine run wild and make errors and say, okay, the final answer will be correct, we need to be able to explain why it gets a certain answer. And that is a big problem today in the industry, because even with ChatGPT, as some of the answers it gives, somewhat questionable, and the creators don't know why it's giving those answers. So I think hardware has a role to play in this, or low-level software has a role to play in this. And we can make these systems more explainable and more deterministic and more debuggable. And as part of this, I think the solutions are going to be a mix of hardware and software. So even in a university like this, where you don't have big hardware resources, right? Like we can't train a GPT-3 model here, because just the amount of compute, we don't have it. But we can contribute to the software part of it. And in a way, it's mirroring the way Linux developed, right? The most expensive data centers in the world today are running Linux, and some of those components actually were written in Sri Lanka. And they are critical to how they interact with the hardware, with how containers work, with how the orchestration works, and so on. And in fact, the people who build the hardware now, they try to follow the specs that Linux has set. So because if they deviate from it too much, then Linux won't work and nobody will buy their hardware. So it's the tail wagging the dog. In terms of low-level software, compilers, the runtime, I think there's a lot of interesting contributions that can be made. So that was all I had today. So just in conclusion, so the evolution of the hardware from CNNs to ChatGPT is along three axes. There's the compute density and efficiency. There's the memory speed and and capacity, and then the connectivity between the two elements. And then I talked about some anecdotes about how we solved some of these problems and how we discovered some of these problems, like rounding, for example. And going forward, it seems like what we have now are going to be, or is going to be, the building block for future AGI systems as well. But the question is, how do we scale to that level? But the building block is the same, but it's like like a house of cards. We have the cards already. We don't know how to build the house yet. But the challenges again are in the hardware software co-design, and there's a lot that we can contribute to that, and we can also contribute to making the hardware and the system itself more deterministic and more explainable. Okay. Well, any questions? Comments? Rules of thumb around partitioning the memory?
Yes. Or partitioning the data, model precision or data precision approaches. Is there any recommendation how to approach it?
I don't think there are any rules of thumb as such. lately, the model parallelism seems to be more popular, but I think that swings. So it's as the system scales, that optimization point changes. So when we had one GPU or one TPU and multiple compute units within it, then it was more data parallel. And now, because the communication delays increase between different sockets of GPUs, then we are favoring model parallelism. But now, as we improve that communication, then it might shift again. I think these terms, these are just terms, right? Ultimately, what we are doing is matrix multiplication, and it's about understanding how matrix multiply works and how you can break matrix multiplication in different ways, right? You can break it row-wise, column-wise, or a mix of the two. So it's that basic understanding of linear algebra is, I think, it's yeah.
So, for the purpose of hardware design, in Nvidia, I don't know, maybe it's already used, generative AI, is it in use, like, let's say, given these constraints, constraints that come up with this sort of hardware design that will reduce the use of that get heated and like that sort of approach. That sort of approach in
So if I understand your question correctly, you're asking why don't we use AI to generate the hardware that will run the AI better? Yeah. Yeah. So I think that's a very good question. Basically, is can I take my job away by giving it to an AI? And no, it's a good question. And I think there are people who are working towards that. Google actually has published a paper. Is a very small subset of that where they're doing the placement part of a chip. So it's not, but it's a start. And they actually showed that they got some 20% improvement in efficiency by doing just the placement of the blocks in the silicon differently. So as we go towards a more abstract problem like how to design an AI chip so that you solve the power problem, it's very hard even to specify that to the AI right now. Right, so that's the challenge there. So we're starting with smaller components. I'm sure the day will come where that can happen, and maybe not for another decade or two, but that can come. But my suggestion would be that we have to take small steps to get there because we are nowhere close to that now. So one is this thing is doing the placement part. There's also some efforts at verifying the design. So once you have a design, it's one of the hardest problems in VLSI is how do you verify that this actually addresses the intent of the designer. And so then you don't have to generate something, but you still have to generate the verification collateral that tests the design. So there's a lot of research on that. Well, there is some research on that. I don't know the state of that, but I do know that the placement part was published and they showed about a 20% improvement.
I have one more follow-up question. When it comes to Sri Lanka, do you think it's difficult to do that sort of hardware sort of problems because of the resources and since we are not a terrorist country, even in that case, can't we design it here and sort of outsource manufacturing part of it?
Yeah, I mean, I think the design part is definitely possible. It's just a matter of fostering the talent here and growing it. There is a company here, I forget their name, who do FPGA designs. Maybe you know their name. Yeah. So it is in a sense happening already. They do FPGA designs and they manufacture there. I mean, the actual manufacture part, even in America, it doesn't happen, right? We build it and send it to Taiwan, and TSMC builds it. So the design is the name of the game. But even to do the design, the tools and the infrastructure needed is quite expensive. So maybe that's what you're referring to. And yes, I mean, that's a problem, but again, you start in small steps and it's possible. And at some point, I think, because now there are a lot of tools available on the cloud, so there's no upfront investment. You just have to pay the operational cost, and then you can do that kind of design. But I think a better place to invest is actually in the hardware-software co-design part and the low-level software. And most of the answers are going to be in that, in the runtimes and compilers and the management layers. And there's a lot of innovation there. Sure. Thank you for the question.
Very nice presentation. Thank you very much.
Thank you.
So going forward, as you mentioned, there is of course this barrier between transmitting data between processing and memory. Even with this factor, I think that will retain
Yes.
for a while. So going forward, what do you think? Like as you mentioned about the power consumption also, what are the trends available, and what do you think about, and what will be the timeline in that direction?
So that's there's no clear answer now. Some people have tried with different memory technologies, like MRAMs and things like that, but none of them have really panned out. It's very hard to compete with the existing solutions, and they have had various problems that have prevented them. And then there are others who have tried this thing that, the broad category of techniques called in-memory computing or near-memory computing, and then there's even this one company that does analog computing in the memory. They take advantage of the nature of our memories today, and they do essentially the multiply add in analog. And again, none of that has really worked out because there are issues with accuracy and precision that you just can't beat digital. Yeah. So far the basic tried and true way seems to be winning out. So it's hard for me to say where it will head, but as you said, the gap is increasing. We are going to have to do with it. I feel that it's going to be addressed more algorithmically and in the software rather than with new hardware technologies.
Any other questions from the students? Yeah, go ahead. Yeah, please. Use the mic so that it's easy.
So when it comes to machine learning and deep learning and those kind of area, so in software development, when we are changing to a new system, we always try to support the legacy system, but we leave them after like a 10 or 20 years kind of thing. But in kind of machine learning things, when we install a TensorFlow, we just install the required CGD and CUDA, and then when the upgraded version, or when we want to change the TensorFlow version, we have to change the CUDA and CGD version installation also. So these things changes within 2-3 months, like kind of thing. So the reason might be, what I thought was that the infrastructure behind the CGD and CUDA was not established well. That's why that the reason that every changes are like 2 months changes, we have to switch to different versions of these things. Why is that such a change in small time period?
So the question is that the infrastructure like CUDNN and TensorFlow, they change often. They change every 2-3 months, and that is causing a problem in terms of you have to upgrade and modify your software accordingly. So the question is, why is that happening? I don't have a good answer because I don't work directly on the product side, but my suspicion is that a lot of the software is, it's being constantly optimized, because as we understand hardware problems, unlike in the CPU world where we have a good understanding, we actually develop the software even before the CPU is ready. In the GPU and neural processor world, it's being constantly upgraded and optimized and trying to make the best use of the hardware, addressing problems like the memory distance problem that was referred to earlier. So it is normal for those to upgrade. However, it's supposed to happen in a way that they call it's app compatible. So previously we had this thing called backward compatibility, where you can take something that you run on iPhone 12 and you can run it on iPhone 13 or iPhone 14 because they are backward compatible. Now they have something called app compatibility, where they say, okay, you have to change, you might have to change cuDNN and others as the hardware changes, but the application need not change. So they are supposed to maintain that interface. So if they are not, thank you. If they are not maintaining that interface, then I'm not sure why that is. Maybe we can talk afterwards about the exact issue. Yeah.
It's pretty good. They're asking what's the take up for industries for a developing country like Sri Lanka in making investment in AI. Is it a viable path for prosperity?
So I think there's two ways to look at it, right? AI is new to everyone. I mean, there's a few years lead for America and China and all those, but broadly it's new to everyone. We are still at infancy. So in that sense, it's an area where we can compete, and the primary currency to compete in AI is still brain power, right? It's not, there's no established thing. Money to some extent, yes, but I think it's still brain power. So in that sense, it's still a lot of theoretical work, a lot of algorithmic work. So I think there's potential there to compete, and at least within Sri Lanka, you are not fighting against so much of any established players. So, there's room to do things in AI that we haven't even done yet. Kind of like when cell phones came, the third world, actually, the uptake of cell phones was much more than in the developed countries. So AI can be in that way as well. But there's a broader problem that everyone is facing, even in the US. The smaller universities complain about the bigger universities having access to all these computer resources, because even to train a reasonable size model, you need a lot of compute. So I think for that, that's going to be a challenge. And access to that kind of hardware, no one is going to give it for free, because it's just the operating cost of running these big GPU data centers is very high. So it's not that they have an upfront capital cost and then they give it for free. So because the operating cost is high, it's going to be hard for even others to give it to us for free. So that's a challenge, and I don't have any answers for that. But I think the opportunity is great enough that we should not shrink at that challenge.
Thank you. That's the question. There were a couple of comments that people are happy with the talk and our next meeting start. There was another question. Let me see if I can read it. Sure. While I just, any other questions for the audience here? Yeah.
So, coming from transformers, no matter how much we train in parallel, during inference it has to be sequential, right? Because in training we use attention mask to hide the future and train in parallel. But in inference we have to know so far what has happened, what has to be the next word, right? So at inference, it has to be a sequential, right?
It is still not sequential in the sense that it's not going word by word the way a human does. It is digesting everything it knows so far in parallel, even in inference.
Say the translation task. During training, it has both the target and source.
Correct.
But during inference, you have only the source. So at least the inference part, it has to feedback whatever it has generated so far into this thing, just like an RNN, and then generate the next possible.
Correct. Yeah, but it has already been trained. So the model already knows from its training what to expect. The input, like when you ask it a question, the entire question goes to it in parallel. And you can try to confuse it by asking the question in different ways, but if it works correctly, it will understand the context of the entire question because the entire question is fed to it in parallel. But you're right, it can't see the future like it does in training, and that is where the accuracy of the model comes in.
There is a question in the chat that we talked about ChatGPT, when a new technology or tool comes into the market, it creates hype and there will be discussion around it. After the bubble pops, the technology or the tool becomes normalized, go out of the spotlight. But I see reason for it too because people have a higher expectation, and that could be the reason why it quickly sort of fade out. The question is that does this impact the roadmap of a company, like a vision or a roadmap of a company, how they should handle this kind of pop-ups?
So that's a more broad question, but I think let me address the ChatGPT part. So yes, I think it is overhyped. Right, I said it, but behind the hype there is something, right? It's not it's not nothing, right? There is something. There is fundamental technology there, and people are already using it in very interesting ways, right? You guys are probably more familiar with than I am, but I speak to people sometimes, and I'm surprised at the kind of use that they are putting it to. And they're using it in some places, for example, to teach English and so on. So it is hyped. It's not. It's not the next level AGI intelligence or anything. It's not sentient or anything like that. But it is a useful tool, and the great companies are built by how they adapt to these useful tools that come along once every decade or so.
Any other questions from the audience? You can go ahead now. You can use the mic for everybody.
Pardon me?
Can you hear me?
Yeah.
So in the transformers, after the sequence will be transformed into the numerical forms, the sequence of features will be divided into different gates, right? The multi-gate attention is there, right?
Yeah.
So after dividing the features into multiple gates, the following computing is occurring in each gate, right? If we take a transformer, there will be 12 gates. I don't think you are in the field like people.
That could be a software question. Maybe
I didn't understand the question. So between the multiple heads, what was the question?
If you take a transformers, there will be 12 attention gates inside the transformer architecture. So in order to optimize the hardware, they are dividing the sequence of features into multiple gates and into the computation.
Are you saying, are you asking if they are parallelizing it based on the attention heads? I don't think that's how it's parallelized today. Actually, I don't know how it is parallelized, but I don't believe it's based on the attention heads.
But I'm asking why they are dividing the features into different gates. Because if you divide the sequence of features into different gates, the context will be lost, right? reduce the computation power or
So I don't know how it's partitioned today, but if they are partitioning it based on heads, that would be one of the questions I would have too. And I think there would be some other problems with that as well, because I don't think that would be a sensible way to do the model parallelism. But again, I don't know how it's partitioned, so I'm sorry, I don't have an answer for you.
Performance of the transistors. You mentioned that we are off by a factor of around 1 million. So, and speaking of transistors, we are slowly reaching the limit, theoretical possibility of a small transistor. So, in future, will there be a basic building block replacing transistor, and if so, will it alter the whole architecture that we are seeing now?
So the question is, I said earlier that we are off by about a factor of 1 million for reaching brain-like capacity, but we are reaching the limit of transistors already. So what's the future plan for addressing it? So first of all, I threw that factor of 1 million in there, but nobody really knows how far we are away from the brain. So take that with a grain of salt. But we know it's a large number. We are not close. Second is, so how will we get there if the transistors, there is a limit to how small we can make the transistors, and more importantly, there is a limit to how many transistors we can turn on and off at a time, because that takes power. That drains electrons, and that means something is getting heated, and that heat, it's hard to get it out. Already we need to put water, some sort of liquid cooled system to extract that heat. So we don't know what the next technology is, but there have been other solutions. One of them is that we are using multiple sockets connected together, more like a high-performance computing rig, and that's why the communication architecture becomes much more important. So you can get about a factor of 1,000 to 100,000 that way. And if you want to go beyond that, yes. Right now, we are working in sort of 3 nanometer size transistors. Will be, we can see a path to get to something like 1 nanometer, or maybe a little less than that. But once you get into the angstrom level, there's a limit to how much you can go. Right? We are talking about size of atoms and size of the silicon dioxide molecule. So so far, we have had this good trajectory. I have faith in the industry that they'll find a way to get past that as well. But I don't know what the next technology is. These are all really great questions, by the way. Thank you. It's it's great to see the level of insight behind the questions.
One last question before we wind up. All right, good. So, truly appreciate the time and thanks for coming here. It's a pleasure to have you. And I really like the way that how you showed the history. It's a very quick, summary of the literature, and also give a very big picture of some of the technologies like the autoencoder, comparing from feedback into model versus feedback into these things. So that's give a very nice picture for them to understand. I think I'm going to steal that slide for my lectures as well. So thank you for doing that, and thanks for the time, Mr. Aingaran. I appreciate you coming here. Actually, we had a very, very successful event. We have close to 300 participants in the Zoom, that including various universities and industries. Some of the industry leaders are over there. And we already got the feedback, and it's like everybody's happy with the topic and they're happy with the presentation, asking for videos, they want to share it. So we will sort that out later. So truly appreciate that, and thanks to the audience. I mean, some of these people, like the final year, they are working on ML projects. and they are here, and some of them are masters students and PhD students are here, and the faculties have leave because probably have lectures now. So again, thank you so much, and truly appreciate you spending this time.
Thank you for having me.